Hello class. So we're talking about Markov chains in this lecture. Topic I love. First studied it, actually I guess first came across it in mathematical modeling class in undergrad. People were using, I think in that example, it was like maybe modeling events in a baseball game, because that's sort of a discrete sport with different states, like man on first, two men on base, whatever. So anyway, there's ways that you can model that. And then I saw it again in graduate school in a couple pages in one book in a advanced linear algebra class. And then I ended up stumbled upon doing it for my research, for my PhD, because it's deciding. I went to an advisor and was like, I don't know what to work on. He's like, well, I work on Markov chains. I was like, okay. And so since then, I was doing a very theoretical thing at the time, but I've just gotten more and more interested in them because they have so many applications. At the time, I didn't see some of that. I was working much more on theory. Okay, so what's a Markov chain? We'll start with the example you see a lot of books. We're not going to use the big whiteboard. I think most of this will be, we'll do some online stuff, so screen shares. Okay, so you'll have something called P, which is usually the notation for a transition probability matrix. And then you'll have states, and often they do these with the weather. So let's just take a little tiny textbook example. Suppose states are sunny and cloudy, and you want to know what's the probability, maybe have some historical data that you move from sunny to sunny. So that would be this element here, 0.6. And then from sunny to cloudy, maybe 40% of the days that happens. So this is a one-step transition matrix, right? I'm going from states to states. So today, tomorrow, you can think of it that way. Notice that all the elements in the row sum to 1. It's a stochastic vector in each row, and therefore it makes it a stochastic matrix, which just means these are probabilities between 0 and 1. They could be 0, they could be 1, and the row has to sum to 1. Okay, so you can do things with that transition probability matrix. And so let's go to an example. Share the screen. And all these things I've put in your Oaks module. So this particular web page, someone produced this really cool analysis. Again, Markov chains can be used to analyze games. This we'll just do a sort of toy example here with the game of Chutes and Ladders. So if you're not familiar, the board looks like something like this. It's a 10 by 10 grid, so there's 100 spaces, and they've decided to number them this way. It doesn't matter, that's up to you. I've never played the game, so I don't actually know if these numbers are pure in the game. And then there are players roll dice to get onto the board. Say I rolled a 3, I'd start here. And then when it's my turn again, I'd roll. And maybe I get a 6, so I would end up 1, 2, 3, 4, 5, 6, 9. But when I landed on 9, there's this ladder that advances me quickly to 31. So you want to get on the yellow ladders because the goal is to get all the way to 100. What the red are what are called snakes or chutes, they send you backwards. So, you know, in theory, it's possible you could just be very unlucky, and keep following chutes back. You want to try to get to the ladders. Okay, so there's some chance here, and then there's some structure to the game, and we can actually model this. We can think of it, they talk about as a directed graph, and we'll see that matrices often represent graphs. They can be weighted or unweighted. We'll talk a bit more about that. So you can follow through, read this about the game, but we're going to get to the part that has to do with Markov chains. Okay, so here is our from and to. So here's a ladder that takes you from 1 to 38. So that's your from state and your to state. So all the ladders are described, and all the snakes or chutes are described. They take you backwards. There's one from 98, and that takes you down to 78. And then we'll also talk about, they were wondering how long does it take on average to play the game? Like if there's a couple players, are we sitting there talking about hundreds of turns, thousands of turns till someone makes it to 100, because there's a chance you could keep following those chutes. Okay, so there's Andrei Andreevich Markov. Love this guy. He made some really cool applications, and we'll talk about his initial applications in a bit. But the thing about a Markov chain, it is this transition probability matrix that is stochastic. It has the property that it's memoryless. So what we're going to understand by that is when we power this P matrix, p squared, p cubed, those are the probability that given today it's sunny, that 3 days from now, if I look at p cubed, 3 days from now, I look in those elements in the matrix, whether it's sunny or cloudy. P to the 100 days from now, if I want to look at the weather. Now it's memoryless because it's only looking at the state before to figure that out, right? I'm taking p squared times p, that gives me p cubed. I didn't take advantage of like, well, if it's been sunny for 45 straight days, there's a chance it's going to rain or be cloudy, I guess I should say, in this example. So it's only looking at the previous state. So that's that phrase memoryless. It's only looking at the state before. Okay, so let's get to the Markov chain part of this. Okay, so they filled out just a little sub matrix of this. So we're looking at rows 10, 11, and 12, columns 8 through 19. And the probability, if you're at 10 to advance, they're saying it's 1, 6, 1, 6, 1, 6 if you're just doing it by rolling. But you have to remember that there's chutes and ladders. So now let's look at a different part of the sub matrix and see how we fill that in. If I was on square 17, 18, or 19, if I'm on 17, I'm looking at this sub matrix of the P transition probability matrix. I'm looking at columns 8 through 30. And from 17, there's a chance right here I could roll. There's a 1/6 chance I could roll a 3 and land on 20, which sends me back to 9. So that's how we get the 1/6 there. But there's a chance I could roll a 1, a 1/6 chance I roll a 1 and move up to 18, a 1/6 chance I move to 19. Again, 20, I don't really land on that because I go right back to 9. So that's why it's a 0. And then there's a chance over here at 23 that I wouldn't land on 23. So I had rolled a 6, got to 23, but immediately shot up to 28 with the ladder. So there's a 1/6 chance. So we're going to fill in this transition probability matrix in this way. The author of this page has already done that for us. That's great. And then he talks about what happens when you get to 100. I think he says in the game, maybe you have to roll exactly onto 100, but he's going to make a simplifying assumption and say you can roll past that. You can have 101, 102, right? So you have to land exactly. And so he doesn't show it here, but we want to think about what happens. So there's ways to roll into 100. He gives those probabilities. So those would be the columns of how you can get possibilities to get into 100. But what happens when you get in 100? Well, 100, you don't leave, you don't go anywhere. So what you would do to fill that out is you'd have all zeros and then a 1 right here for 100. So that's a different kind of state. We haven't seen one of those yet. And we could have done it over here. I'll just change this example for a moment. Let's say in this transition probability matrix for the weather that when you started in a cloudy state, there's a 100% chance you stayed cloudy. So this row is a stochastic vector. It is a stochastic matrix, but this is what is called the state. So these are states, sunny and cloudy. The states here are the numbers on the board, 1 through 100. Those states can either be what are called transient states, recurrent states, or absorbing states. So just think about transient, you're just going to pass through that state temporarily, you don't stay there. Recurrent, you could come back to it. So many transient states are also recurrent. If there's a possibility like that 9, we could come back to it with a chute. And then what I just described as state 100 or state cloudy is what is called an absorbing state. Once you get there, you never leave. Right? So all the probabilities are absorbed there. And you can measure things like time to absorption. How long does it take us to get to absorption? And that's really what this page is about. So he describes the transition matrix. He puts in a dummy node 0 for you're off the board, then you have to roll onto the board. So really he's looking at 101 by 1 matrix. Okay, and then he talks about, well, you can power this thing, matrix multiplication. We learned this last semester on cube. Well, there's a lot of smarter ways of getting these transition probabilities for higher dimensions. We'll talk about that later when we get to Markov chains. Okay. Okay, so what he's showing here, this is a pretty cool graphic. Each one of these square big grids is the matrix, and the density, darkness of the red dot is your probability, and it's a number between 0 and 1. The neat thing about this, when I start powering the matrix, and we'll do this in MATLAB in a moment, p squared, p cubed, p3, they're always stochastic matrices, so they're always going to have probabilities. So the numbers in any p to the n power is always between 0 and 1. And so therefore, he's plotting these on darkness. So like this pink one is much lighter. There's less chance that we land here. And so he's powering the matrix and seeing what happens in the long run. And you can see as they're playing, like you're progressing up the board, right? So there's, okay, most of the probabilities here. There's little chance that you, in 4 steps, that you could have gotten here. Right? This is p to the 4th, is what he's showing. This is the matrix p to the 5th. He's showing visually, not with all the probabilities in it. You keep on going. And in the 7th game, there's a small probability you could be almost near the end, but most of the time you're sort of in the middle here, simulating this. Okay, 10 rolls, here's 20 rolls. Large chance that the game is over, but there's still some small probabilities that people have gotten unlucky and followed suit. So you're back down here. So there's no down here. But he's saying by 100 rolls, there is no pink in this matrix. Dark red here, that's a 1. P to the 100 for this matrix has all the probability right here in the 100 by 100 slot. Okay, he's got some animations, a little more graphs. What's the probability to finish the game by 100? Almost completely, because again, those percentages are 0.5% or something. So almost all the time you finish the game in 100 rolls. Okay, then he does some examination of sensitivity changes. What if some of the rules change? Pretty cool to take a look at those, because you do have to do that for your assignment. Okay, so next thing I want to do. So that's one application. So we did weather, chutes and ladders, and now let's go to MATLAB. Okay, and I added some stuff. Most of you in class last semester are familiar with MATLAB, but if you're not, I did add some tutorials on how to get it. It's free to all students in the College of Charleston. I have a 6-minute video on how to download it. And then I have 4 small short PDF files on how, the short tutorials on how to use it. Check those out, do as much as well as you need. But we're gonna be doing a lot of stuff with matrices this semester, especially in this module. So if we wanted to enter that weather one that we had, 0.6, 0.4, so that's the first row, semicolon means go to the next column, and then we have something like 0.3, 0.7. So this is just getting it in there. We can see that if we multiply it by 1s, which is the vector of all 1s, each row sums to 1. So this is a way to check when you're inputting bigger ones for your project this week to make sure that they are stochastic, because you might be printing out something that's much, much bigger, like the chutes and ladders, which is 100 by 100 matrix. It's an easy way to check. But we can do things like this, p squared. Now, again, it was sunny, cloudy. So this is the probability. The first row tells us that there's a 48% chance that if it's sunny today, 2 days from now, it would be sunny, given that I believe this data up here, right? And given that it's sunny today, 2 days from now, there's a 52% chance that would be cloudy. And so you can keep on going. Cubed. Right, and we can maybe just jump ahead. And you'll see that they start converging. This happens often. And in fact, so vocabulary we've learned: stochastic, transition probability matrix, transient state, absorbing state, recurrent state. We didn't have any absorbing. All of these states, the 2 states in this example, were both transient and recurrent, because you could come back to them. And when the Markov chain is something called ergodic, which means every state is reachable from every other state, which it is here. And you can do that from checking out this. Is there a path from sunny to cloudy? Yes. Is there a path from cloudy to sunny? Yes, there's always a way. And so easy ways to check that, just search on, is a matrix irreducible? Is it ergodic? And if it is, then you're guaranteed that in the long run, you're always going to have a matrix with just one row that's repeated over and over. And that's called your stationary vector. That says in the long run, we converge to these stationary values. We don't leave from these, they're stationary. Once we get here, we never leave. And so this is saying in the long run, Almost 43% of the days are sunny and 57% are cloudy, regardless of where we started from, right? It doesn't matter whether it was sunny or cloudy how many days ago. So these are what are called your stationary probabilities, stationary vector. Not every Markov chain will have those, but most of them do, again, if they're organic, which is irreducible. Okay, so just a few things in MATLAB that you can do. You can also check the eigen, and we have this in your this week's assignment. You can ask for the eigen values and eigen vectors. Let's see, I have to do that something like this. Call the vector D. Okay, so these are the eigenvalues, and you'll always have an eigenvalue. One, you're guaranteed. You're also guaranteed the eigenvalues are always non-negative. Really cool properties of Markov chains, which are prone for Rudin's theorem, things you'll learn in linear algebra or advanced linear algebra. And they also have vectors. But let's look at, I shouldn't have done P, I should have done P transpose. And then in that case, if we take one of these and normalize it, so let's do these. The second row, all columns. That's what that means. Let's just call this S for stationary. We'll get that vector. Oh yeah, and I have to normalize it. And I'm forgetting all these steps here. I don't have my eigenvalue. I want to get the dominant one. So let's see. I need to get the one corresponding to one. I think they might be columns. Oh yeah, maybe it's this column. So I actually should have done. Okay, so there it is. There's our stationary vector. It's actually the normalized version of the dominant eigenvector of P transpose. So P transpose dominant eigenvector is here because that corresponds to the dominant eigenvalue of 1. And that is those same P to the infinity power, right? That's the stochastic probability we're saying. 43% of the time it's sunny, 57% of the time it's cloudy. So you can get those by powering P. Why am I saying this? Powering P could be expensive. Matrix multiplications, ln cubed. You don't want to do P times P times P, or even P to the 4 times P to the 4. You know, you don't want to have to be doing that. There's a way to get the eigenvectors with something called the power method. Really fast. It's just vector matrix multiplication, O(n) squared. So you can get it much more efficiently if you're doing really big ones. For your project, even if you had 100 by 100, no problem. MATLAB can do P to the 100. No big deal. But if we do the second half of the semester and you want to continue with one of these projects, then these efficient computational ways are important. Okay, next thing. Okay, let's talk a few examples here. I'm trying to make these videos efficient. Stuck to 20 minutes. So some things for your project. So you guys are going to have to think about something you want to model with a Markov chain and then answer. There's 3 or 4 questions in there you have to answer. I'm going to ask about what happens when you power the matrix, what happens if you power the long term, do a sensitivity analysis. So people, again, in the past, just give you some ideas that might help, have done some really neat models. One student, Michael, got really interested into modeling hurricanes. So think about hurricanes, they actually do have states that they go through. Tropical storm then becomes like a level 1, becomes level 2, and so on. Are there any absorbing states in that case? Which ones are transient, which ones are current, which ones are absorbing? He was able to get historical data from the National Hurricane Center or something like that. He ended up adding more states and really refining it and making a semester-long project. I mentioned Markov. So Andrei Andreevich Markov, he was doing this in the 1900s, over 100 years ago, early 1900s, was, I think, 1906, was taking analysis of language, like what's the probability that an A follows a B? What's the probability? And so he used his states with the letters. So for us in English, like a 26 by 26, or if you add some punctuation, maybe up to 30 something matrix. And he wanted to know, and he actually did this all by hand. He read a bunch of several pages of Russian authors and filled in the transition probability matrix, each of those probabilities by hand, and then started powering that thing also by hand. So amazing computational ability back then and persistence to do it, but he was just driven to figure this out. Now, what could that do for you? Some students in the past, now that we have computational ability, were able to take that and say, what if I wanted to make like a random word generator? So you'd have roughly a 26 by 26 matrix. Maybe you add a space that's the end of the word to 27 by 27, and you could try to feed in those probabilities somehow. So you're gonna write code that would strip that off and feed in a whole bunch of words or a bunch of text, paragraph of text, and then figure out what would be a random word that a particular author, if you fed it in only stuff from a particular author, you can figure out random generation of words. Other folks have done this for like sentence generators as well, because you can make the state's words. You say, well, that's huge, there's a lot of words, but actually in English language, there's about 400,000. And if you just use common words, you probably really narrow that down. So it's totally doable. Other students have thought about this, again, probabilities and the states being pages in a book for a choose your own adventure book. So they thought about this as like a graph. That's another good idea. And in fact, the Chutes and Ladders had a hyperlink to thinking about this. Chutes and Ladders as a graph as well. So they thought about choose your own adventure book as a graph. And there was an absorbing state at the end where you terminated, you finished, they all ended up somewhere or several places. It could be, I should say, you'd have more than one absorbing state too. That's interesting. In a chain, you can measure the time to a particular absorbing state. So this graph and path through there with probabilities that they figured out. This consulting company I'm working with, XCures, is thinking about cancer treatments. And for a patient, they often go through, again, think about it as a graph, there's different treatments, and they often go through different sets of treatments. And so they might historically look at the path that 100 different patients have taken through these treatments that then generates a transition probability matrix, which you can then analyze. New patient comes in, it's in this particular state. What's the probability that they will end up in this? And then maybe you need, given shortages with treatment, how do you go get that? Where should we send them? And then the last one I want to talk about is PageRank. So this is a really cool one. I spent a lot of time writing some books about. Oh, before I do that, let's share the screen and just show you some stuff in books. Google. Class. Okay, so I've put some stuff in module 2, which is about Markov chains. Again, the tutorials I mentioned on getting MATLAB and getting started with it. It's 2 videos there, 6 minutes and 32, a bunch of PDF files associated with learning MATLAB. You can use anything you want though in this class. If you know R really well, you can do transition matrices and powers of matrices in Excel. That's another great option. Do what you know, but also if you want to learn something new and you want to take this project longer term, keep those in mind too. Okay, and then the Chutes and Ladders, there's the link to the website, a PDF version of the website. I'm going to talk about PageRank, link to that talk. That's what I'm about to do now. And then lastly, your assignment, I'm going to drop in right here. Okay. So let me share the screen one more time and we will. Go to this talk. Okay, this is a talk I gave many years ago. Random search order results, how search engines and mathematics organize the web. Run through this real quick. So in 1998, mathematics transformed web search. So what happened back before then, again, a lot of you have no recollection of what life was like pre-Google and pre-MSN and some of these great search engines. So I'll tell you what I had to do in college. I had to go on something like this. This is in Gopher, and it was crazy when I just blew my mind when I realized I could be sitting at Mount St. Mary's Library in Emmitsburg, Maryland, and get a paper, and it looked in this ugly sort of text version, right, from University of California, on a topic that I needed for this philosophy class I was taking. It was just crazy that, like, how the hell is this getting here? But it all came through this not very friendly graphical user interface. And the main tool that search engines used back then was just what's called an inverted index, which is a whole lot like an index in the back of the book. For every topic or search phrase, right? If you want to know, one of my books has a step about absorbing Markov chains. If you wanted to find out where that was, this would tell you it's on page 185 of that book. Except for the web, they want to know what is the web page. So the web pages all got ID numbers, all the search engines gave them ID numbers and started cataloging like this. And so when you come in and enter your search engine on aggregated chain, it would go to this list and find, oh, there's web page 197. And it would serve that back to you. Problem was with this inverted index, clearly there's way too many pages. Instead of like 6 things listed here, there's like 6,000, like 600,000, right? You've seen that for some of the searches you do, right? Just for this very specific search that I'd enter for that particular talk that they asked me to give, there's 2,000 for a very obscure thing. You could easily be spammed by these indexes too, because human eyes are different than spider eyes. So when this was a particular page for that, when a human looks at it, it looks great. But this is what the spider that's crawling the web for Google looks at, and looks at the HTML and reads this. And it's easy to hide stuff in here that isn't seen by the human. Like, this could be how a human might look at this particular, if this were a web page, but the spider might see things like this, all this sort of spam that's hidden in the background, and they would do like a white font on a white background. Easy to hide it, easy to spam. Even though the human never saw the spam, the spiders thought the page was about these sort of things, right? When an eye popped. It's data, huh? Okay, so then in 1998, so before that, everything was just looking at the text on a page. And then after that, everything started adding. If you didn't do this, you couldn't compete. You weren't a search engine. They started adding a link analysis. Okay. Every search engine does that. I happen to know that because they wrote this book. I think serve as a consultant in this court case. Look under the hood of all the major search engines. Be paid to do that. Get to go look, fly out to New York, fly to California, look at their search engines, sit in front of a machine for 3 days, for 3 hours. That was what they were. 8 hours a day for 3 days was the limit. And they're allowed to poke around in the machines and got to see everybody's doing link analysis. Okay, so what is this link analysis? So when you do a search in Google, there's sponsored results, and sometimes they appear over here, and then the peer results. We're just going to focus on the peer results. Okay, yeah, we have those rankings are important. Okay, here's the stuff that has to do with Markov chains. Well, we can actually think about the web, tiny little web, just 6 pages, but you know there's gazillions, right? Every node here is a web page, and each arrow is a hyperlink. Okay, so there's a hyperlink from 1 to 3, from 3 to 1, from 1 to 2, and so on. So we can build this, and that's what the crawlers do. They automatically go out and crawl. They go to web page 1, they follow all of its outlinks, and they just keep on doing this continuously. And they go and read the text material on this page. We already talked about that. And then they add this link analysis. They have this giant graph, and it's actually not stored as a graph, it's stored as an adjacency list, but we'll get into that. Web pages have both inlinks and outlinks. And so they quickly found that it seemed that the inlinks were more important than the outlinks. Like when I make my homepage, I can outlink to anybody, but it's harder for me to solicit people to inlink into mine. And so they decided that inlinks were votes of endorsement from one page to another. We'll skip this, I don't have the video clip. Okay, so here we go, random walk on the graph. We are going to take a random walk on the graph because that's how Google thought about this. They thought about a web surfer, and they would, when they were at web page 1, they would flip a coin, and 50% of the time they go to web page 2 and 50% to web page 3. That's the random part. So they said, suppose we just took a random walk, which is often what we talk about associate with Markov chain, a random walk on this graph. And so from 3, we could have gone to 2 or 5. The coins then go to 5. From 5, we could have gone to 4 or 6, flip the coin, and up at 6, and so on. And we keep watching this guy and seeing what happens. And we'll explain what that means in a minute. So here's the matrix notation for this. So that process of a random walk on the graph can be described with this matrix. So from web page 1, I had half the probability I go to 2 and a half to 3. So I fell off that first row. Web page 2 didn't go to anybody. It saw all zeros. That's going to be a problem, right? This matrix is not stochastic yet because we have what's called substochastic, because this row 2 is a problem. Okay, when he gets to 2, what does he do? He's stuck there. So this is what they called a dangling node, and they fixed it by adding a link to anybody else with some small probability. And they call this teleporting their sci-fi fans brand page. And this is equivalent, they said, to just like going up to the, like it actually does have a modeling mechanism that when you go to the URL bar, sometimes you just totally type in URL and jump. You don't always follow the hyperlinks. Sometimes you add links. So here's what the matrix becomes. We add, it's equally likely to go to any other page on the web, including where we're at. So 1/6 times everybody. Now the sum of these is now a stochastic matrix. Skip that. Okay, but there is another problem. Let's look at this set of nodes down here, 4, 5, 6. They don't ever go back to anybody else. They create a cycle or a set of nodes that you can never leave. They had a solution for that. They added what's called full teleportation. So they didn't go try to find the cycles because that would be problematic and expensive. They said, let's just add this chance that 1/6 the time you'll teleport anyway. So first we fixed that one dangling node. We had a stochastic matrix, but we could have cycles. And in fact, you can see in the structure here, this all zeros and then this block here. This is a cycle. But again, didn't want to try to find those. So let's just fix it easiest possible way, make a simple solution, teleport some percentage of the time. Well, what percentage of the time? They decided to use this number. They've since changed it and slid it around. A lot of research on this, what is called a parameter, the alpha parameter of Google's PageRank. 85% of the time you follow the hyperlinks, 15% of the time you teleport. Again, you can change that. It affects the convergence. It slightly affects the stationary probabilities. Okay, but what we're going to do is just observe where Randy, which pages are on. So this is a video clip, but we would just be doing this, observing Randy, which is the same thing as getting this matrix, add these two together, and you have a P matrix. It is stochastic. Stochastic plus a linear combination of stochastic and stochastic is stochastic, or convex combination, I should say. So the sum of these is a P matrix. We could power it. It's small enough for this example. Of course, Google isn't going to power a billion by a billion matrix. They don't even store it as a matrix. That's a whole nother talk. But for us and for this week, Markov chains, you could get this 6x6 P matrix. You could power it and see what is the long run proportion of the time that a random surfer would spend in any particular page on the web. And I don't think I did it in this talk, unfortunately, but so that would just be taking this matrix, putting in MATLAB, powering it, and you get your stationary probability vector. And that would tell you how important a particular page is, because if a random surfer kept coming back there often, it must have mean he was pointed there by other important pages. That's their whole thesis. So really what Google is doing is getting the stationary vector of a giant Markov chain. Again, the mathematics behind that is amazing, the computational science and all that, another talk. But the idea of it is something you understand after this week's lecture on Markov chains. Okay, so here's a quick summary. They get a search query. They pull out all the relevant pages from the index, and then they rank those pages by their page rank, which is the stationary vector of our Markov chain. And that is what is presented to you. Oh yeah, they're doing the world's largest eigenvector computation, which is cool if you take linear algebra, you understand that. A few more places you can go for resources. There's so much more. Let's see. A few things at the end here. PageRank, that's now been like 20, 25, 20 some years ago. And it's still being studied. There's like hundreds of papers every year about that. I think that's what it is. Yeah. So many papers about that PageRank. Because it's such a simple, elegant, and powerful algorithm, PageRank is a sum of other PageRanks pointing into you. It's a simple concept of weighting by the quality of the voter. Like I could have 6 inlinks, but if they're all from, if you're thinking about letters of recommendation, let's say, if I got 6 letters of recommendation, but they're sort of anonymous, not very well-known people, or got one from, say, Bill Gates, that might carry a lot more weight. So that's really what this is saying. The PageRank of a page is the PageRank, the sum of the PageRanks of incoming pages. So if you have inlinks from important pages, you're also important. Okay, then another neat thing is why this is still studied. You can think of it as a Markov chain. You can think of it as an eigensystem, as a dynamic system, as a linear system. I've done all that, written a whole book about those. Think about it as a graph, a network. You can do quantum mechanics on it. And those are just some of the eigenvector systems. Oh, this really cool thing because PageRank has some parameters that can be tuned. The one we talked about was teleportation, but there's plenty of other ones. So these little knobs that people like to turn and analyze and study and see how that changes the ranking. If it doesn't, or which parts of the ranking it changes, by how much. You can study the convergence of this. You can study ratings versus rankings. You can try to approximate how good are your approximations. Literally just thousands and thousands of papers about this. So you see these kind of charts all the time. Then the other thing, just join this on the scale that they are doing it. So that was their original idea when they were in graduate school. They were your age, pursuing a master's, going to go on for a PhD, decided to quit because they started the company Google, didn't go back. That was then, it was a giant Markov chain. Now they're doing it with graph theory techniques because it's just the web has exploded and grown and grown. Yeah, this is the size of the web, and it's exponential growth, and that was an old number. Oh, and then it's still being studied because there's constantly spam. People are trying to profit off of it, so you're always fighting that. And there's just a gazillion applications. The PageRank gets used all over the place. We've used it for March Madness. Okay, I think that's enough on that talk. All right, I think I covered everything then. So Markov chains in 36 minutes. Have fun this week. It's going to be good.